So in section 7.3, we're going to take our next step with our radicals. And so we're going to look at two rules for working with radicals. In fact, these are kind of things people assume to do anyway. So we're just going to kind of put words to what you would assume. So the product rule of radicals says this. If you have two roots, notice this, okay, when you're doing this, the index is the same. So if you have two radicals that have the same index, this does not apply to different indexes, and they are real numbers, n is a natural number, all of that is just defining the terms, then the following thing is true. If I have the nth root of a number a times the nth root of a number b, sometimes it's more convenient to do the multiplication first, the a times b before doing the root. So it's just saying your order of operations here does not matter. On the left side, you're doing the roots before you multiply. On the right side, you're doing the multiplying before the roots. Just depends on what situation you're in. And we're going to do both over the course of the next couple days. So the first couple of examples we're going to do, we're just going to apply this in a very straightforward fashion. So here's my example one. Example one says I got the square root of 5 times the square root of 7. So I want to write this under one radical. So that is going to be the square root of 35, there you go. So we just take both of those numbers, 5 times 7, since they were under the same index, a square root, I can then put them under one radical. Okay, you tracking with me so far? If you're not, let me know. That's why we're here. Do exercise 1, please. So when you do exercise 1, again, I want you just to get in the habit noticing that both those indexes are the same. And so then I get what as my answer here? Yep, square root of 77. Well done, beautiful. So there we go, square root of 77. My next exercise that I have for you right below that, exercise 2, I just want to make the point with this that when you are multiplying, you don't cross over. You multiply coefficients by other coefficients, and you multiply the stuff under radicals by other stuff under the radicals. You don't cross over. So give that one a try, see how you do. So firstly, what do we have outside the radical here? 2 times 6. What's 2 times 6? There you go, thank you. And then under the radical, so we're going to have a square root. And what do I have under the radical? 15, great. So what's outside the radicals stays outside. What's under the radical stays under. It's good so far? All right, the next problem, I'm just throwing a variable in there so that you see that and you don't get discombobulated. So go ahead and do exercise 3, please. Okay, once again, same index, nothing's different, so it's a square root. And what did you write underneath the radical here? Perfect, it would be 10xy, great, okay? Nothing is outside the radical, everything is underneath the radical. Okay, 2 more examples. The only reason I threw these other examples on is not because I didn't think you'd be catching on by now, but just because I wanted to make sure I put a couple with other indexes on. So go ahead and do both exercise 4 and exercise 5. And then we'll compare notes in just a few seconds. And so the first one, bless you, just want to make sure I make note of this. When you are multiplying your radicals, you do not touch the index at all. This is a cube root, this is a cube root, so your answer is going to stay a cube root. So put a little 3 in the basket. It's not a coefficient, okay? So it's just in the basket, and then 4 times 5, that's 20. And then the last one that you did, I asked you to go ahead and do both of them. The last one, we've got 4th roots. Again, 4th root. So that's great. My answer is going to be a 4th root. And then when I multiply what's under the radicals, I got 5 times 6 is 30. I've got a t, and I've got an x to the 3rd. All right, so that's our primer on the product rule of radicals. We are going to use that some more in different ways, but that's the basic introduction. We feel okay and comfortable with it so far. All right, well, then the other property of radicals that we're going to mention here, whenever there's a product rule, we've always got to have a quotient rule. So the quotient rule says something super similar. It says if I have two roots, again, with the same index, okay, your index is a natural number. I'm never going to mess with you on that. Then the following is true, and it says the same thing. If you have a radical in the numerator and a radical in the denominator, then you can go ahead and put one radical and do the division underneath. So it's order of operations. On the left, we're taking the roots first and then dividing. On the right, we're dividing first, taking the roots. Okay, doesn't matter the order. And in fact, we've already applied this. You've already used this, and I did not tell you it was a thing. When we talked about taking square roots of fractions, if you remember, I told you you can consider the numerator and denominator as separate things. That's just the quotient rule of radicals. So my example right here, I've got the square root of 7 over 36. Well, notice in the numerator, square root of 7, there's no whole number. That times itself gives you 7. So what I'm going to do is I'm going to use the quotient rule of radicals to simplify this. I'm going to have square root of 7 in the top, square root of 36 in the bottom. Now, you never need to write this. I understand that most, if not all of you, could have done this problem without writing that step. I just want to show you how we're applying the quotient rule of radicals. The numerator, I can't do anything with, so it's going to stay square root of 7. But then square root of 36, what times itself gives me 36? 6. Great. And now there's no more radical. Remember, once you identify that number, once you have taken the root, it disappears, just like a plus sign would when you add. Okay. So no, don't put a radical in the bottom. All right. Do the same thing with exercise 6, please. Okay, I'm guessing most of you did not write this step, but I'm going to again for the first couple just to remind us that we're using the quotient rule of radicals. We did this in section 1, okay? So I'm just separating and saying I can consider the numerator and denominator independently because of the quotient rule of radicals. And then the top, the square root of 49 is 7. The bottom, square root of 36 is 6. So far, are we so good? Before I turn the page, anybody got anything that I'm unclear of? Am I moving too fast? Am I doing anything wrong here? Yeah, I'm amazing, I know. All right, gonna flip the page, page 2. All right. I would like you just to do the next 2 exercises, 7 and 8. They're just applications of the quotient rule of radicals, just to make sure that we get enough examples under our belt, and then we're gonna talk about the next thing. So exercise 7, again, I'm applying the quotient rule of radicals. You don't have to write this step. As long as you can accurately get the answer, I'm fine with it. If you struggle, then write the step, okay? Use a little extra ink. I've got plenty of pens if you need some. Okay, so square root of 3 in the top, square root of 144 is 12. Uh-oh, red alert, red alert. Can I cancel the 3 and the 12 here? Why not? Yes, the 3 is under the radical. The 12 is outside the radical. They are different things, okay, just like we did when we multiplied. So if you did that, that's why I'm mentioning it, okay? So don't beat yourself up. It's okay. Just don't do it again, okay? So you cannot cancel something that's under the radical with something that's outside. That answer's done. Over here, I just gave you a problem that had 4th roots instead of square roots. So in the top, I got the 4th root of t. In the bottom, I've got the 4th root of 16. Can't do anything with the numerator. So whatever you did, that's your answer in the top, the 4th root of t. In the bottom, what number times itself 4 times gives me 16? There you go, 2 outside the radical. All right, so in general, very basic. That's the product rule, that's the quotient rule. Any questions yet? So what we're going to do next couple days, okay, is we are going to, various situations, apply these two rules. And so what we're going to do next is super important. Okay, probably the most important thing that we'll do, as far as your short-term future in college algebra in this unit is learning how to simplify radicals. So if you don't know how to do this, this is something to focus on. Okay, so for instance, all along when we've been dealing with our radicals, we've been simplifying things like square root of 25, and we said, oh, 5 times 5 is 25, so that's equal to 5, or we just did this, square root of 36, okay, 6 times 6, but we know there's lots of numbers between 25 and 36. Okay, do I always just leave them, or is there anything that I can do? So for instance, my example that I'm going to do is the square root of 20. Now, we can't do this with every number, what I'm about to tell you, but we can do it with some numbers. What I'm going to do is I'm going to simplify this. And my process for simplifying is asking myself this question. Okay, whatever number that is under there, is there a perfect square factor of, and in this case, it's 20. Now you might be thinking, perfect square, what is that? You haven't used that term before, Perkster. Okay, well, I'm just going to go over to the left part of this, or excuse me, the right part of this. I struggle with my left and my right. And I'm just going to write down real quick some of the perfect squares, which if I had a band, that would be my band name, but that's okay. Okay, so these are the perfect squares. And this is not an exhaustive list. I'm just getting us started. But the perfect squares are all of those numbers that we get from multiplying the same thing times itself. So I'm going to start with 2. 2 times 2 is 4. 4 is a perfect square. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. Now I'm having too much fun. 7 times 7 is 49. 8 times 8 is 64. I'm going to go just a little bit further. 81, 100, 121. I'm just going to put some dots because you can keep going forever and ever and ever. So what your goal is to ask yourself, and you've got calculators, so it's not intended to be too big of a challenge, is there a number on this list that divides evenly into 20? I heard one person. Anybody else going to take a stab at it? Sure. Okay, I heard 2 people say. Okay, so 20 is this. Okay, instead of a 20 under the radical, it's going to be 4 times 5. Now you might be thinking, hey, Perkster, why did you pick 4 times 5? Why didn't you pick 2 times 10? Are either 2 or 10 on this list? No, 2 or 10 does not do me any good. Okay, you have to pick something that's a perfect square. And then what we're going to do, and again, once you get good at this and you've done several of them, you don't have to write this step out, okay? But I'm going to, for the first few, now I'm going to use the product rule of radicals. The product rule of radicals says instead of having them both under the same radical, I am going to split them apart. So I got square root of 4 and square root of 5. And now, what's the square root of 4? 2. Is the 2 under a radical anymore? No, because we have taken the square root. It's outside. Square root of 5, is there a whole number times itself that gives me 5? No, 5 does have a square root. It's just an irrational number. So since it's irrational and it never ends, I'm not going to write it down. So 2 square root of 5, that's my answer. The 2's outside the radical, the 5 is under the radical. All right, so we're just going to practice this for the next 3 or 4 or 5 problems because I'm assuming you haven't seen it. If you have, even better, you're ahead of the game. So exercise 9, please simplify the square root of 45. All right, so 45. Does 45 have a factor that's on my list of perfect squares? Perfect. That's great choice. I'm just going to write the 9 first, but it doesn't matter the order at all. That's just my personal preference. So 45 is 9 times 5, both under the radical. Again, once you've done a few and you get good at this routine, you don't have to write this step. I'm going to use the product rule of radicals now, and I'm going to separate them. And now the square root of 9, what is it? 3, no longer under a radical because I took the square root. Square root of 5 stays under the radical. Done. Anybody have a trouble with that? Anything that you're unclear of that we need to talk about more? All right, then try the next one, square root of 50. A lot of you seem done. So if I'm rushing you, let me know, but I don't want you to sit there bored. So what's the perfect square factor of 50 on my list? Okay, it's 25. Beautiful. Well said. I appreciate that. So 25 times 2. So again, product rule of radicals says I got square root of 25 times square root of 2. And the square root of 25, 5. Square root of 2 stays square root of 2. It's an irrational number. So I represent it in the exact form square root of 2. Okay, one more square root, and unless there's any objection, we're going to move on to the next thing. So square root of 700. All right, what's the number on my perfect square list? That is a factor of 700. Yep, 100 times 7. I'm just going to stop for a second. The reason I picked this number is sometimes a student might say to me, hey, Perkster, 700 is 4 because you're just going using your calculator and you start at the beginning of the list. I get it. I understand why. And you say, hey, it's 4 times 175. Could I have used that? And the answer is totally. You can start there, but you have to make sure you simplify these things completely, like reducing a fraction. So then you would say from there, if you did start with 4 times 175, because you just started at the top of the list, then you would say, oh, is there a perfect square factor of 175? And there is. It's 4 times 25 times 7. Okay, and you're going to end up with the same answer as I end up with. You just did it in 2 steps instead of 1. That's totally fine. So I'm going to go back up here. I'm going to do product rule of radicals, square root of 100 times square root of 7. Square root of 100 is 10, and then square root of 7. So far, so good? All right, well, my next 2 examples, I've got one for me and one for you, just to show us each that we can do the same thing with cube roots. Okay, this process isn't limited to square roots. Most commonly in this class, we'll be dealing with square roots, but we could do this. Now, this time, remember, before my question was, is there a perfect square factor of 20? When I've got the cube root, I want to know, is there a perfect cube that goes into 24? And if you don't know what the perfect cubes are, feel free to make a little list. Okay, I can come over here. You can do it in like 2 seconds. So here's some perfect cubes. So 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. And then 4 3 times is 64. 5 is 120. You can see the cubes get big real fast. I'm going to stop there. Is one of these numbers on this list a factor of 24? Yeah, 8 is. So I'm going to use that. Okay, so again, just to be clear, because this is a common question, and I totally get it, because we were just dealing with square roots. Common question is, why didn't you use 4? Perkster, 4 times 6. And the answer is, 4 is a perfect square. If this was a square root problem, I would have used 4. You're right. Okay, but this is a cube root problem, so I'm going to use 8 times 3. Just make sure you're paying attention to your index so that you know. So then the cube root of 8, I'm using the product rule of radicals, cube root of 3. Cube root of 8 is 2, and then I've got the cube root of 3. So one for you. Is there a perfect cube? Which there is. I'm not giving you a little joke that I'm going to sit here and laugh at you while I try to find out. What's the perfect cube factor of 54, and then simplify it. All right, so again, don't be afraid to use your calculator, okay? You can't break your calculator by doing a lot of division problems on it. So what is the perfect cube factor you figured out for 54? 27. Yep. Okay. 27 times 2. Great. Product rule of radicals says I can split that apart and give them each their own radical, so I will. And then the cube root of 27 is 3, and then times the cube root of 2. There we go, there's my answer. All right, so we still feeling okay? Okay, that's an important skill. Please practice that. Be ready. There's going to be a bunch of problems like that on the test because that's something I want to make sure that you come away from this class and you go to your next class that you understand how to do. Okay, the next thing we're going to look at is, okay, all these problems we've done have had numbers under the radical. Can I have variables? And that's a great question. The answer is yes. That makes life even more fun. So we are going to look at what happens when I have variables under my radicals. So answer this question for me. If I have the square root of x squared, what times itself gives me x squared? Yep, okay, we're just going to x. Well, then we're going to do a bunch of even numbers, and we're going to see if there's a pattern that develops. How about x to the 4th? What times itself gives me x to the 4th? Yep, 2 plus 2 is 4. Remember, we add our exponents when we multiply. How about x to the 6th? What's the square root of x to the 6th? Okay, 3 plus 3, so that's x to the 3rd, yes. One more, we're going to make a big leap in number here. X to the 20th, what times itself gives me x to the 20th? Okay, 10 plus 10, so x to the 10th. Notice, what did we do to the exponent each time to get its square root? Yeah, we divide by 2, which hopefully maybe something clicks in your brain. That's what I think we would expect because the index is 2. Remember, the index becomes the denominator of a fraction. So you just divide by 2. So we're linking together a couple different things. So I want you to take a moment. I'm going to give you like 24 seconds. Do exercise 13 and 14, a couple of examples of taking square roots. You've got some even exponents. All right, so the square root of x to the 26, what you write down for that? Yep, 13 plus 13 gives me 26. And then the next example I just put on there because it doesn't matter how many things you're multiplying together under the radical. The product rule of radicals says you can consider them differently. I'm not going to write that down. So we're just going to go one at a time. How about the square root of x to the 18th? What's that? And y to the 42nd? Yeah, and I do the same thing. I get it. So y to the 21st. Okay, can I turn the page? We doing okay? Any follow-up questions? All right, I believe this is our last page on this one. Oh yeah, we're doing great. How much fun are we having? Okay, so then the last thing for us is, okay, Perkster, this is all great. We did numbers, we simplified, we just did even exponents. What happens if my exponent's odd? So I've got the square root of x to the 7th. Do I just write down x to the 3.5? The answer is no, we're not going to do that. Here's what we're going to do. We're going to apply the product rule of radicals just like we did before. And anytime you see an odd exponent that you're taking the square root of, what we're going to do is we're going to rewrite this And what I'm going to do is I'm just going to pull one of those x's out so that I create something with an even power. So I'm going to call this x to the 6th times x to the 1st. You always just pull one out. Okay, it doesn't do you any good to pull 3 or 9 or whatever. So we're just going to 1. 6 plus 1 is 7. I've not changed the problem. But what I've done is just like when we did the problems on the previous page, the square root of 50. What I've done is I've created a product where I can take the square root of one thing, and then the other thing I'm just going to leave under the radical. Okay, so product rule of radicals says I've got square root of x to the 6th times the square root of x. Square root of x to the 6th, you already answered that question for me. That's x to the 3rd. That's on the previous page. And then I have square root of x. Does that seem like a reasonable process? Okay. We pulled one of the x's out so that I would have something that's divisible by 2. And then I was able to take the square root. So go ahead and try exercise 15. It's the same, pretty much exact thing. Okay, when I rewrite what's under the radical, what'd you do? Okay, I'm just going to write the y to the 14th first, but it's totally fine if you wrote it the other way. Y to the 14th times y. I took one of the y's and set it to the side so that I would have something with an even exponent. And now the product rule of radicals says I can consider these two things separately. And so then the square root of y to the 14th, that is y to the 7th. It no longer is under a radical because I performed the operation. And then the square root of y stays under the radical. Try exercise 16. It's the same thing. We're just practicing. All right, when I rewrite what's under my radical, how did you write that? X to the 24th times x. Fantastic. Great job. By the way, the reason I picked the number 25 here is, and I get this, you're just learning all this. Sometimes students see the 25 and it's a perfect square and write down that the answer is x to the 5th on this. But remember, we don't multiply exponents. We add the exponents. Okay, so that's why I picked that number. It was intentional, just because I didn't want you to fall into my web of deceit. Okay, so make sure you maintain that awareness that we treat exponents differently than coefficients. So the square root of x to the 24th, I'm going to apply my product rule of radicals times the square root of x. And then the square root of x to the 24th is x to the 12th. The square root of x stays what it is. And there we go. All right, exercise 17 is the last one of these. And I just put both. You got a coefficient to simplify and you got an x to simplify. Okay, so on this problem, we've got the 18, we've got the x to the 21st. We've done both of these things separately. Now we've just combined them into one problem. So the first thing I'm going to do is write my radical. Let's forget about the x to the 21st for just a minute. 18, what is the perfect square factor of 18? Okay, 9 times 2, so I'm going to write that here and here. And then now I'm going to forget the 18 for a moment, and I've got the x to the 21st. How do I break x to the 21st apart to simplify it? x20 times x. Okay, I just want to stop there. We're doing the same thing that we've been doing, but we've just combined it into one problem. So I know it seems now like a very monstrous thing. Okay, but it's the same process we had before. Okay, and so now the product rule of radicals says I can consider each of these things separately. So what I'm going to do is I'm going to take the square root of the things I'm able to, and I'm going to leave the stuff that I can't under the radical. Okay, so let's do this. Square root of 9, what's that? Okay, so I'm going to write a 3 right here. Can I do the square root of 2? So I'm going to leave a little gap here. Square root of 2. Square root of x to the 20th is what? X to the 10th. I'm going to put that outside the radical. And then this last square root of x, I can't do anything with that. Stays under the radical. Everybody tracking on why the final answer is written the way it is? Are we still doing good? Okay, in fact, we're doing pretty good. I want to do one more of those just because I know there's a little harder. I see a lot of people writing and rewriting, so I just want to make sure that I'm just not glossing over something. So before we do the last little bit of this section, let's do this. I would like you to simplify, let's say the square root, and let's just have a fun number. What's that going to be? Let's try this 162. It's not as difficult as it seems. Okay, and then let's do x to the it's just hard to think of novel numbers, 23rd, and then let's do another one just to make this as spicy as possible, and y to the 15th. All right, so 162, what's the perfect square factor of 162? Yeah, it's 81 times 2. And then x to the 23rd, how do we break that apart? I'm sorry, x to the what? Okay, 22nd, great, times x. Remember, we always just, when we're taking square roots, we just remove 1 so that we have an even power. And then y to the 15th is going to be, so once again, just like the previous problem, my final answers, I'm going to write the stuff I can take the square root of outside the radical. I'm going to leave the stuff I can't take the square root under the radical. So starting the 81, square root of 81 is 9. Square root of 2, it's going to stay under the radical. Everybody with me so far? Okay. Square root of x to the 22nd. Square root of x. And then y to the 7th, yes. And then the y. Does everyone see, okay, before I leave this, y, this stuff's outside the radical, this stuff's under the radical. We understanding that? Okay, because that honestly is the most common mistake on the test, is people reverse the order of that. Once you've taken the square root, it goes outside the radical. Okay, so the last thing for this section is as follows, what's called the Pythagorean theorem. I'm sure, I am 100% certain all of you have seen this in some sort of middle school geometry. In fact, in this class, we're not going to go any deeper than that, but I will, spoilers, the first day of college algebra, if you have me, or if you have anybody, we're going to do this again because we finally, at long last, do something interesting with the Pythagorean theorem. Okay, so that will happen on the first day of class in college algebra, and it's something that you'll use several times throughout. So just I'm no more spoilers. I just want to leave you with anticipation. So what the Pythagorean theorem says is this, okay, Pythagoras, Greek mathematician, cult leader, all sorts of good stories about Pythagoras. Says if you have a right triangle means that you have a 90-degree angle right there. So it's a special kind of triangle. This relationship does not hold for just any triangle, although if you take trigonometry, there's a more general relationship that you'll talk about that would lead to the Pythagorean relationship. Again, no spoilers, but lots of fun stuff. Just for terminology, when you're reading problems, these two sides that border the right angle, okay, these two sides right here are called the legs of the right triangle. And then the longer side right here, that's opposite the right angle, that's called the hypotenuse of the triangle. Okay, I'm not going to quiz you about terminology, but it's always good to have that in your back pocket. The traditional letters historically that have been used for the sides of the right triangle, so I'm not going to break tradition. You use A and B for the legs, and you use C for the hypotenuse. And then the reason this is, one of the reasons it's so popular in the math world, this is called one of the foundational mathematical equations, just because it's of its simplicity and its use and things that can be derived from it. It's this relationship right here. It says if you square each of the legs and add them together, so a squared plus b squared, and that equals c squared. And the way Pythagoras would have written this is Pythagoras didn't have that notation. They thought about multiplication in terms of area. So he would have said the area created by the square, a square of this length and a square of that length is equal to the square of drawn for the hypotenuse. So he had to prove it with geometry. There's a really cool algebraic proof that we'll look at real briefly in college algebra. So it's just one of those foundational things. So all we're going to do with this really cool little formula that you've seen before and probably don't have any appreciation of because it just looks really ridiculous is we are going to use it to find the unknown side, and it allows us to apply radicals. So I've got an example, you've got an example, then we're done with this section. So example 7 says we're going to find the unknown side. I don't know the hypotenuse of this, but I do know the Pythagorean relationship, so let's set it up. So first, give me one of the legs that we're squaring. What is it? 5. Okay, 5 squared. Perfect. Plus, give me another leg. 8 squared. And then that's equal to what in this particular case? Okay, c squared. Great. So the next thing I'm going to do is actually do a little arithmetic here. So 5 squared is 25 and 8 squared is 64. I don't think any of that is too challenging for you, especially since you got calculators. We're going to add 25 and 64 together. 25 and 64 gives me 89. Now, this is something we'll talk in a little more depth in college algebra, but all you need to know is the following. If I have c squared equals 89, I don't want c squared. I want plain old c. What am I going to do to both sides of this equation, would you guess? Not square. Take the root, square root. Okay, so I'm going to take the square root of this side. I'm going to take the square root of that side. Square root of c squared is c. The square root of 89, now here's where this comes into play, is if you can simplify that at all, you will. And in fact, on your example, you're going to be able to. 89 is a prime number, so my answer is going to be just square root of 89. Something you'll learn in college algebra is that when you impose a square root on a problem, there's two answers actually. There's a positive answer and a negative answer. I'm overlooking that here since we're talking about a length of a triangle. So we're just going to deal with the positive one. Okay, but I'm just forewarning you about some fun stuff that you'll learn about a semester from now. Okay, so exercise 18, final problem from this section. Do it and enjoy it. All right, so here we go. Remember the legs, I square them equal to the hypotenuse squared. So this one, if you noticed, I gave you slightly different information. So we've got the first leg is 6, I'll square that. The second leg is b, I will square that. And then the hypotenuse is 12, I will square that. Doing my arithmetic, 6 squared is 36, plus b squared, 12 squared is 144. I just gave you this problem because this is the two styles you're going to see. Either you don't know the hypotenuse or you don't know one of the legs. So on this one, what do I have to do first before I worry about the square root? Yeah, I got to subtract that 36. So we'll do that. And when I do that, I've got b squared is equal to how much? 108, you said? Okay, trusting you. Okay, 108. And so then I'm going to take the square root of both sides, just like we did on the previous problem. Again, I'm going to ignore the negative answer just because that we're dealing with geometry here. So the square root of b squared is b. And now 108. Does 108 have a factor on my perfect square list? Sorry, I heard a no and I heard what? 36. Okay, so I'm going to go with 36 because I'm pretty sure I planned the problem that way. So just make sure you go far enough up the list that you're not avoiding one of the factors. So 36, and it's 36 times. Perfect. Sounds great. And so my value of b, the length, square root of 36 is 6, and then square root of 3. All right, before we close the book on this section, does anybody have any final thoughts or questions or concerns? All right, then I am